For 1,000 of years of human existence, our visual memory of the world was completely fleeting. An image entered the human eye, struck the retina, and then faded forever into the subjective recesses of human memory. If someone wanted to preserve a face, a landscape, or a historic moment in time, they had to rely entirely on the fallible hand of an artist holding a paintbrush, a charcoal pencil, or a sculpting chisel. But in the early 19th century AD, human beings achieved something that had previously belonged only to the realm of fantasy and magic. They figured out how to force rays of light to paint their own permanent, razor-sharp picture onto a polished plate of silver. The daguerreotype was born, and the world was never the same again. The invention of photography was not the overnight flash of inspiration of a single solitary genius working in isolation. Instead, it was the grand convergence of two completely independent scientific disciplines that had been developing along parallel tracks for centuries: optics and chemistry. The optical half of photography, the ability to project and focus rays of light into a crisp, two-dimensional image, had already been solved and perfected for hundreds of years before anyone figured out how to capture it. To understand how humanity first learned to trap a shadow, we must journey back over 2,000 years to the ancient world, where humans first observed the magical properties of light passing through a tiny hole in the dark. In the 5th century BC, the Chinese philosopher Mozi was sitting in a darkened room when he noticed something extraordinary. Light passing through a tiny pinhole in a wall projected an inverted, upside-down image of the outside world onto the opposite wall. Mozi correctly deduced that light rays travel in perfectly straight lines from their source, crossing over each other as they pass through a narrow opening. Around the 4th century BC in ancient Greece, the philosopher Aristotle made a similar observation during a solar eclipse, noting how the crescent shape of the partially covered sun was projected onto the ground through the tiny spaces between the leaves of a tree. While ancient thinkers noted this curious optical phenomenon, it was not until the 11th century AD that the underlying physics were rigorously tested and documented by the pioneering Arab mathematician and physicist Ibn al-Haytham, known in the West as al-Haytham. Working in Cairo, Egypt, around 1021 AD, Ibn al-Haytham conducted groundbreaking experiments with darkened rooms, lanterns, and pinholes, publishing his discoveries in his monumental 7-volume work, The Book of Optics. He coined the term that would define the medium for centuries, the camera obscura, which translates from Latin as dark chamber. Ibn al-Haytham proved that vision occurs because light rays reflect off objects and enter the eye, or an aperture, in straight lines, laying the mathematical foundation for modern optics. By the late 16th century AD, Renaissance scholars and artists had transformed the camera obscura from a full-sized room into a portable scientific device. In 1558 AD, the Italian polymath Giambattista della Porta published a widely read treatise recommending that painters use a camera obscura to trace perspective with mathematical precision. Around this same time, opticians made a pivotal improvement. They placed a convex glass lens into the aperture. The lens allowed vastly more light to enter the chamber while keeping the projected image razor-sharp, transforming a dim, blurry projection into a bright, vibrant, living image of reality. During the 17th century AD and 18th century AD, instrument makers miniaturized the camera obscura into portable wooden boxes equipped with adjustable brass lens tubes and 45-degree reflex mirrors that bounced the image upward onto a sheet of ground glass. Master European painters, including Johannes Vermeer in the Netherlands and Canaletto in Venice, used these portable reflex camera obscuras to trace complex architectural details, reflections, and perspective lines with uncanny precision. By 1800 AD, humanity possessed cameras that were optically almost identical to modern photographic cameras. Yet there was one agonizing limitation. The image on the ground glass was merely an optical ghost. The moment the subject walked away or the sun set, the image vanished without a trace. The optical problem was completely solved, but the chemical problem remained an unsolved riddle. To capture the fleeting image, humanity needed a chemical substance that could react to light and permanently remember what it had seen. For centuries, alchemists and apothecaries had observed that certain minerals and silver salts darkened over time, but they universally assumed that air, heat, or humidity caused this degradation. The breakthrough in photochemistry finally arrived in 1725 AD, when a German professor of anatomy and polymath named Johann Heinrich Schulze made an accidental discovery in his laboratory. Schulze was attempting to create a phosphorescent glow-in-the-dark material by dissolving silver in nitric acid and mixing the solution with powdered chalk inside a glass flask. When he placed the flask near a sunny window, he was amazed to see that the side of the mixture facing direct sunlight rapidly turned a deep, dark purple, while the side in the shadow remained bright white. When Schulze shook the flask, the dark layer mixed back in and the whole mixture returned to white, only to darken again on whichever side was exposed to the sun. To prove that the reaction was caused by light and not heat, Schulze placed the flask next to a roaring fire where no color change occurred. He then cut out paper stencils of letters and pasted them to the outside of the flask. When exposed to the sun and the stencils were removed, the dark shapes of the letters appeared perfectly etched into the chalky mixture. In 1727 AD, Schulze published his findings, demonstrating to the world that silver salts are photosensitive, darkening purely in response to light. In 1777 AD, the brilliant Swedish-German chemist Carl Wilhelm Scheele took Schulze's work a step further. Scheele synthesized silver chloride and exposed it to a solar spectrum produced by a glass prism. He discovered that the violet and blue ends of the spectrum darkened the silver chloride much faster than the red or yellow ends, establishing the first scientific understanding of photochemical sensitivity across different wavelengths of light. Scheele also discovered that ammonia could dissolve unexposed silver chloride while leaving the darkened metallic silver untouched. Scheele held the secret of photographic fixing right in his laboratory, but because his focus was purely on fundamental chemical reactions rather than visual art, he never attempted to use this chemistry to capture an image from a camera obscura. The first humans to deliberately attempt using photosensitive chemicals to capture images from a camera obscura were the English experimenter Thomas Wedgwood and the famous chemist Humphrey Davy. In 1802 AD, Wedgwood, the son of the wealthy pottery industrialist Josiah Wedgwood, coated sheets of paper and white leather with a solution of silver nitrate. He placed flat objects, such as dried leaves, insect wings, and painted glass plates, directly on top of the sensitized paper and exposed them to sunlight. The uncovered areas of the paper darkened, while the areas shielded by the objects remained white, producing the world's first primitive photograms or contact prints. However, Wedgwood and Davy hit a devastating chemical brick wall. Whenever they brought their finished prints out into normal daylight to inspect them, the entire surface continued to react to the ambient light, darkening uniformly until the image was completely swallowed by blackness. They tried washing the paper in water and treating it with various chemical baths, but they could find no way to stop the reaction. In an 1802 AD scientific paper, Davy wrote with deep frustration that nothing was lacking to make the process universally useful except a method of preventing the unshaded areas from being colored by daylight. Unable to find a fixing agent and suffering from chronic ill health, Wedgwood abandoned the project and died in 1805 AD at just 34 years of age. While the English experimenters struggled with silver nitrate, a quiet, obsessive French inventor living in the Burgundy countryside was preparing to approach the problem from a completely different angle. Joseph Nicephore Niepce was born in 1765 AD into a wealthy aristocratic family in Chalon-sur-Saône. Niepce was a lifelong inventor who, along with his brother Claude, had patented the pyreolophore in 1807 AD, one of the world's very first internal combustion engines, which successfully propelled a boat up the Saône River. But in the 1810s AD, a new artistic craze swept across France that completely redirected Niepce's creative energies: lithography. Lithography, invented in Bavaria in 1796 AD, was a revolutionary printing method that used polished limestone slabs and greasy crayons to reproduce drawings in massive quantities. Niepce became fascinated by lithography, but he had one major handicap. He possessed virtually no artistic drawing talent. His son Isidore initially drew the illustrations for his lithographic stones, but in 1813 AD, Isidore was drafted into the French army to fight in the Napoleonic Wars. Left alone in his laboratory without an illustrator, Niepce asked himself a radical question. Why should a human hand have to draw the image at all? Could he find a way to make the rays of the sun draw the image directly onto a printing plate? Niepce began experimenting with silver salts in 1816 AD, coating paper with silver chloride and placing it inside a small camera obscura he constructed from a cigar box and a microscope lens. He successfully captured faint negative images of the view outside his window, but like Wedgwood before him, he could not figure out how to stop the unexposed silver from turning dark when exposed to room light. Frustrated by silver chemistry, Niepce abandoned silver salts entirely and turned his attention to organic substances and natural resins, seeking a material that would physically alter its mechanical properties when struck by light. After testing various varnishes, tree saps, and gums, Niepce discovered a unique substance known as bitumen of Judea. Bitumen of Judea was a naturally occurring asphalt found in the Middle East, particularly around the Dead Sea region of Palestine, modern-day Israel, that was commonly used by engravers as an acid-resistant ground on metal etching plates. Niepce discovered that this dark, tar-like asphalt possessed a remarkable photochemical property. When exposed to strong ultraviolet sunlight, the bitumen molecules underwent photopolymerization, cross-linking together and becoming insoluble in oil solvents. Conversely, the unexposed areas of bitumen that remained in shadow remained soft and fully soluble. Niepce developed a meticulous chemical process that he named heliography, meaning sunwriting in Greek. First, he ground solid bitumen into a fine powder and dissolved it in oil of lavender, creating a dark, syrupy varnish. He then poured a thin, perfectly uniform layer of this varnish onto a highly polished pewter plate and dried it over gentle heat until it formed an even, golden-brown coating. Next, he loaded the sensitized pewter plate into a sturdy wooden camera obscura fitted with a landscape lens. He placed the heavy camera on the second-floor windowsill of his country estate, Le Gras, pointing out across the courtyard toward a pigeon loft, a pear tree, and the sloping roof of an adjacent barn. Because bitumen of Judea is only weakly sensitive to light, the exposure required an extraordinary amount of time. Niepce uncapped the brass lens and left the plate inside the camera for at least 8 to 20 hours on a bright summer day in 1826 AD or 1827 AD. As the hours slowly ticked by, the sun moved across the sky from east to west, illuminating both sides of the courtyard buildings in a surreal, continuous exposure. When Niepce finally retrieved the pewter plate and carried it into his dark laboratory, no image was visible to the naked eye. He then submerged the plate into a shallow bath of 1 part oil of lavender mixed with 6 parts white petroleum. As Niepce gently rocked the tray, a milestone in human history unfolded. The solvent dissolved and washed away all the unexposed soft bitumen that had remained in the shadows, exposing the shiny, bare pewter metal underneath. But the areas of the plate that had received intense sunlight had hardened completely, remaining firmly stuck to the metal as a raised, matte brown crust. When dried and held at an angle to the light, a clear, permanent image of the buildings, roofs, and courtyard of Le Gras appeared before his eyes. The plate, known today as View from the Window at Le Gras, was the very first surviving permanent photograph taken from nature in human history. Niepce had achieved what no human had ever done before. He had fixed an image from a camera obscura permanently onto a solid surface. Yet, as revolutionary as heliography was, it was far too crude and slow for practical, everyday use. An exposure time of 8 to 20 hours meant that moving subjects, people, animals, and changing weather conditions could never be photographed. Furthermore, the image on the pewter plate was faint, low in contrast, and difficult to view, appearing more like a faint relief etching than a crisp picture. Niepce knew that if heliography was ever going to conquer the world, he needed to find a way to dramatically increase its sensitivity to light. Meanwhile, 300 kilometers north in Paris, another man was obsessing over the exact same dream. Louis-Jacques Monde Daguerre was born in 1787 AD near Paris. Unlike the quiet, scholarly country nobleman Niepce, Daguerre was a flamboyant, energetic, and charismatic artist, theatrical designer, and master entrepreneur. Daguerre had made a massive fortune in Paris by co-inventing and operating the diorama in 1822 AD. The diorama was a giant 350-seat circular theatre where audiences sat in the dark while viewing massive 22-meter-wide hyper-realistic paintings of European cathedrals and alpine landscapes. Using complex systems of pulleys, colored glass filters, shutters, and natural skylights, Daguerre manipulated the lighting on translucent canvas screens, creating breathtaking illusions where a tranquil summer day transformed before the audience's eyes into a raging thunderstorm or a midnight mass lit by glowing candles. To paint these massive, perspective-perfect diorama canvases, Daguerre spent hundreds of hours tracing scenes projected by a large camera obscura. Like so many artists before him, Daguerre was deeply frustrated that the luminous, hyper-detailed images inside the camera could not simply be captured directly onto a canvas without weeks of grueling hand-painting. Daguerre became completely obsessed with discovering a chemical method to freeze the camera's image. He converted a room above his diorama theatre into a chemical laboratory, spending late nights experimenting with various compounds, phosphors, and varnishes. In the 1820s AD, both Niepce and Daguerre were purchasing high-end optical lenses and camera obscuras from the same prominent optician in Paris, Charles Chevalier. In 1826, AD, after listening to Daguerre constantly talk about his secret photographic experiments, Chevalier mentioned that an inventor in Burgundy named Nicéphore Niepce had already succeeded in capturing permanent camera images. Daguerre immediately wrote a polite letter to Niepce, suggesting that they share notes. Niepce was initially deeply suspicious of the Parisian showman, fearing that Daguerre was trying to steal his secret discovery. But in 1827 AD, while traveling through Paris on his way to visit his ailing brother in England, Niepce met Daguerre in person. The two men could not have been more different in personality. Niepce was 62 years old, quiet, methodical, and financially exhausted from years of unrewarded inventing. Daguerre was 40 years old, wealthy, charming, dynamic, and intimately connected to the scientific and artistic elite of Paris. Despite their differences, they recognized a mutual genius in each other. In December of 1829 AD, Niepce and Daguerre signed a formal 10-year legal partnership contract. Under the agreement, Niepce contributed his secret heliographic process and all his technical documentation, while Daguerre agreed to contribute a new camera design and his artistic expertise, with both men agreeing to split any future profits 50-50. For the next 3 years, the two partners exchanged encrypted letters between Paris and Chalon-sur-Saône, testing new chemical combinations to boost the speed of heliography. They experimented with different resins, including the residue of distilled lavender oil, and began testing polished silver plates exposed to iodine fumes. But tragedy struck in July of 1833 AD, when Nicéphore Niepce suffered a sudden stroke and died at the age of 68, leaving his family in severe financial debt. Under the terms of the partnership contract, Niepce's son, Isidore Niepce, stepped in as Daguerre's new partner. However, Isidore had none of his father's scientific curiosity or technical skill, leaving Daguerre to conduct all experimental research entirely on his own. Following Niepce's death, Daguerre made a bold, decisive choice. He completely abandoned bitumen of Judea and all organic resins, realizing that asphalt was fundamentally incapable of the high chemical sensitivity needed for practical photography. Instead, Daguerre returned to the silver chemistry that had fascinated earlier pioneers, but with an entirely new mechanical and chemical methodology. Over the next 4 years, between 1833 AD and 1837 AD, Daguerre engineered a multi-step chemical process that was nothing short of revolutionary. The foundation of Daguerre's process was a composite metal plate made of copper, clad with a thin sheet of pure silver, known as a silver-plated copper plate. The preparation of this plate was an exhausting, highly delicate craft. The photographer had to scrub and polish the silver surface for up to 1 hour using fine abrasive powders, such as calcin and Tripoli powder, pumice, and rotten stone, lubricated with dilute nitric acid and alcohol, rubbing the plate with velvet-covered wooden buffing sticks. The goal was to remove every single microscopic scratch, grease mark, and speck of oxidation until the silver surface became a flawless, pristine mirror that reflected light with total clarity. After the mirror finish was achieved, the plate had to be sensitized in complete darkness. In a dark room lit only by faint candlelight, Daguerre placed the polished plate face down inside a specialized wooden fuming box. At the bottom of the box sat a porcelain dish containing crystals of pure elemental iodine. As the iodine sublimated at room temperature, it released dense, heavy violet vapors that rose inside the box and reacted chemically with the surface layer of metallic silver. The chemical reaction transformed the top atomic layers of pure silver into silver iodide. The photographer, had to monitor the fuming process with extreme precision by catching the reflection of a dim candle flame on the plate. As the silver iodide layer grew in thickness, the plate shifted through a precise sequence of iridescent colors, from pale yellow to deep golden yellow, then to pink, violet, and finally steel blue. Daguerre discovered that the plate reached its maximum photochemical sensitivity when it was a warm golden yellow color. At that exact second, the plate was removed from the fuming box, slipped into a light-tight wooden plate holder, and rushed to the camera obscura. Even with silver iodide, Daguerre faced a massive hurdle. If he exposed the plate in the camera until a visible image appeared by direct photochemical darkening, it still took several hours of direct, blazing sunlight. But in 1835 AD, Daguerre made an accidental discovery that would change the history of science forever: the discovery of the latent image and chemical development by mercury vapor. According to well-documented historical accounts, Daguerre had taken a silver iodide plate that had received only a brief exposure inside his camera obscura on an overcast day. Because the exposure was far too short, the plate appeared completely blank, with no visible trace of an image. Intending to repolish and reuse the plate later, Daguerre placed the blank plate inside a dark chemical storage cupboard in his laboratory. Several days later, when he opened the cupboard to retrieve the plate, he was stunned to discover that a crisp, highly detailed, fully visible image had miraculously materialized across the silver surface. Daguerre was utterly bewildered. He realized that something inside that dark cupboard had acted as a chemical developer, pulling a hidden, invisible image out of the silver iodide. Determined to find the secret agent, Daguerre conducted a brilliant series of elimination experiments. Every evening, he placed a newly exposed blank plate inside the cupboard while removing one chemical bottle at a time. Days passed, and the image continued to develop every single time. Finally, when the cupboard was completely empty of all bottles and jars, the plate still developed. Daguerre carefully searched the floor of the cupboard and found a small dish containing spilled droplets of metallic mercury, or an open mercury thermometer that had cracked. Mercury was the magic key. To verify the discovery, Daguerre designed an ingenious heated fuming box. After exposing a sensitized silver plate in the camera for just 10 to 20 minutes, a fraction of the time required by Niepce, Daguerre placed the plate at a 45-degree angle inside a cast-iron box over an alcohol lamp. The lamp heated a small cup of liquid mercury to approximately 60 degrees Celsius. As the mercury heated, it released invisible, toxic mercury vapors that rose and made contact with the cold surface of the silver plate. The physical chemistry behind this reaction is breathtaking in its elegance. When photons of light strike the silver iodide crystals during exposure in the camera, the energy liberates electrons from the iodide ions, which are then captured by positive silver ions. This forms submicroscopic clusters of pure, neutral, metallic silver atoms, consisting of only dozens of atoms each, scattered across the plate in exact proportion to the brightness of the scene. This invisible pattern is the latent image. When heated mercury vapors hit the plate, the mercury atoms selectively condense and bond with these tiny metallic silver nucleation sites, forming a physical amalgam of silver and mercury. In the bright highlight areas of the photograph, 1,000s of microscopic, frosty white crystals of silver-mercury amalgam grow outward from the surface, reflecting and scattering light in all directions. In the shadow areas where no light struck, the silver iodide remains untouched, leaving the underlying polished silver mirror smooth and dark when viewed against a dark reflection. Thus, Daguerre had transformed photography from a slow printout process into a two-step system, a brief optical exposure to create an invisible latent blueprint, followed by a powerful chemical development step that magnified the reaction by 1,000 and 1,000 series of times. This discovery slashed the required exposure time from 8 hours down to roughly 15 to 30 minutes. Only one final obstacle remained: how to fix the image permanently so that the unexposed silver iodide would not continue to darken and destroy the picture in daylight. In 1837, R.D. Daguerre discovered that he could dissolve and wash away the remaining light-sensitive silver iodide by bathing the developed plate in a hot, concentrated solution of common table salt or sodium chloride. Later, in early 1839 AD, the celebrated English astronomer and chemist Sir John Herschel suggested replacing table salt with sodium thiosulfate, a chemical compound known colloquially as hypo. Sodium thiosulfate formed soluble coordination complexes with silver halides, cleanly dissolving every trace of unexposed silver iodide in seconds without damaging the delicate silver-mercury amalgam. After a final rinse in distilled water and gentle drying over a flame, the image was completely stable, permanent, and impervious to light forever. Daguerre named his new invention after himself, the daguerreotype. In 1837 AD, he drafted an updated contract with Isidore Niepce, pointing out that the new process used entirely different chemicals, different metals, and different operating principles than his late father's heliography. Under the new agreement, the process was officially branded as invented by Daguerre, though Isidore retained a share of future profits. In 1838 AD, Daguerre took one of the most famous photographs in human history from the window of his studio, Boulevard du Temple. Boulevard du Temple is an iconic milestone in human civilization. The photograph depicts a wide, sunlit Parisian boulevard lined with trees, three-story buildings, and shops. Because the exposure required between 10 and 15 minutes of continuous light, the bustling traffic of horse-drawn carriages, carts, and strolling pedestrians moved too quickly to leave any impression on the plate, causing the bustling city street to appear completely deserted, like a ghost town. However, in the lower left corner of the frame, a lone man had stopped on the sidewalk to have his boots polished by a shoe shiner. Because the man stood relatively still for several minutes while his boots were brushed, his silhouette and the shoe shiner were etched permanently into the silver plate, making them the very first human beings ever captured in a photograph. Realizing the profound historical magnitude of what he had achieved, Daguerre sought the assistance of one of France's most influential scientists and politicians, François Arago. Arago was a renowned physicist, astronomer, director of the Paris Observatory, and a prominent member of both the French Chamber of Deputies and the Academy of Sciences. When Daguerre showed Arago his dazzling, mirror-like silver plates in late 1838 AD, Arago was utterly astonished. He immediately recognized that photography would revolutionize every branch of human knowledge, from astronomy and archaeology to fine art and geography. Arago convinced the French government that the daguerreotype was too valuable to be locked behind private commercial patents or held by a single corporation. Instead, Arago proposed that the government of France should purchase the invention outright and present it as a free gift to the entire world. On January 7, 1839 AD, Arago made a preliminary announcement to the French Academy of Sciences, sparking intense international excitement. In the summer of 1839 AD, the French Parliament passed a bill awarding Louis Daguerre a lifetime annual pension of 6,000 francs and Isidore Niepce an annual pension of 4,000 francs in exchange for the complete technical secrets of the process. The climactic moment arrived on August 19, 1839 AD. At a joint, historic meeting of the Academy of Sciences and the Académie des Beaux-Arts at the Institut de France in Paris, François Arago took the stage before an overflowing crowd of hundreds of scientists, artists, philosophers, and international journalists. Arago delivered a masterclass presentation explaining every chemical formula, every fuming technique, and every optical calculation of the daguerreotype process. He concluded with the grand proclamation that France was proud to bestow this miraculous invention free to the whole world, though in a shrewd piece of personal business, Daguerre had secretly secured a patent in England just days prior. The public reaction to the announcement of August 19, 1839 AD was immediate and hysterical, a phenomenon that contemporary newspapers dubbed daguerreotypomania. Within hours of the speech, every optician, chemist, and instrument maker in Paris was completely sold out of lenses, silver plates, mercury fuming boxes, and iodine crystals. Aristocrats, students, and curious citizens dragged heavy wooden cameras through the streets of Paris, setting up tripods on bridges, rooftops, and boulevards to capture views of Notre Dame Cathedral, the Louvre, and the Seine River. The craze quickly jumped borders, spreading across Germany, Italy, Russia, and across the Atlantic to the United States within months. Yet, in 1839 AD, there was still one major limitation: taking portraits of living people was nearly impossible. The original lenses, designed by Charles Chevalier, had a very narrow aperture of roughly f/15, which meant that even in bright sunlight, an exposure still took between 10 and 30 minutes. To sit for a portrait in 1839 AD was an agonizing ordeal. Subjects had to sit outdoors under the blistering midday sun, staring directly into the blinding light with their heads clamped into heavy cast-iron neck braces to prevent any movement. Their faces were often dusted with white flour or chalk to reflect more light. Their eyes watered constantly, and if they blinked, coughed, or swallowed, their facial features became a smeared, ghostly blur. Between 1840 AD and 1841 AD, a rapid series of brilliant scientific breakthroughs solved the portrait problem, transforming photography from an outdoor architectural curiosity into a booming global industry. The first breakthrough came from optics. In Vienna, a Hungarian-born mathematician named Joseph Petzval designed the world's first mathematically calculated portrait lens in 1840 AD. The Petzval portrait lens featured a dual-element design with an aperture of f3.6, which let in nearly 16 times more light than Chevalier's earlier landscape lens, dramatically brightening the image projected onto the plate. The second breakthrough came from chemistry. In late 1840 AD, English chemist John Frederick Goddard and French-born London photographer Antoine Claudet discovered that adding vapors of bromine or chlorine to the iodine fuming box created mixed silver halides, silver bromoiodide, and silver chloroiodide. These mixed halide crystals, known in the photographic trade as quickstuff, increased the light sensitivity of the plate by 10 to 100 times. With the combination of the Petzval lens and chemical accelerators, exposure times dropped from 15 minutes down to just 10 to 30 seconds. The third critical improvement was introduced in 1840 AD by French physicist Hippolyte Fizeau: gold toning, or gilding. After washing and fixing the daguerreotype, the photographer poured a solution of gold chloride and sodium thiosulfate over the plate and heated it from underneath with an alcohol torch. The gold atoms chemically replaced surface silver atoms in the amalgam, which doubled the visual contrast, warmed the cold metallic tones into rich chocolate browns and gleaming highlights, and physically bound the fragile amalgam crystals to the silver plate, protecting the image from oxidation, tarnishing, and mechanical abrasion. With these three innovations in place, the portrait studio boom exploded across the globe throughout the 1840s AD and 1850s AD. In New York City, Matthew Brady opened an opulent studio on Broadway, while in Boston, the master team of Albert Southworth and Josiah Hawes elevated the daguerreotype into fine art, capturing breathtaking portraits with dramatic, Rembrandt-style side lighting. In London, Richard Beard opened Europe's first public photographic portrait studio in March of 1841 AD on the roof of the Royal Polytechnic Institution. The democratization of portraiture permanently transformed human society. Prior to 1839 AD, having a personal portrait made was an exclusive luxury reserved strictly for royalty, the aristocracy, and wealthy merchants who could afford to hire skilled portrait painters. The vast majority of human beings who had ever lived vanished from history without leaving behind a single visual trace of their physical appearance. But within 1 decade of Daguerre's invention, factory workers, immigrants, farmers, and soldiers could walk into a local studio, pay a modest fee, and walk out with a permanent mirror-sharp likeness of themselves or their loved ones. The daguerreotype captured the faces of an entire generation of 19th century AD historical giants. Abraham Lincoln was photographed as a young, clean-shaven congressman in 1846 AD. Frederick Douglass, the brilliant abolitionist leader, sat for dozens of daguerreotypes, deliberately using the medium's undeniable realism to challenge racist caricatures and project dignity, intellect, and moral strength. Edgar Allan Poe sat for his famous, haunting Ultima Thule daguerreotype in 1848 AD, just 1 year before his untimely death. And aging veterans of the American Revolutionary War and Napoleonic Wars sat before the lens, bridging the ancient world of kings and muskets with the modern industrial age. Viewing an authentic daguerreotype in person is an experience unlike looking at any modern photograph or digital screen. A daguerreotype is not an image on paper, but a direct, one-of-a-kind positive etched on a polished mirror of pure silver. Because of its reflective mirror surface, when you hold a daguerreotype in your hands and tilt it slightly, the image shifts between a positive and a negative, depending on how the ambient light reflects off the metal. When you look into a daguerreotype, you see the reflection of your own face peering back at you from behind the eyes of an ancestor who lived 2 centuries ago. Because the silver mercury amalgam image was resting directly on the top surface of the plate without any gelatin or emulsion binder, it was as fragile as the dust on a butterfly's wing. Even a light brush of a human finger or a soft cloth would instantly wipe away the image forever. Furthermore, exposure to the sulfur in normal air would rapidly tarnish the silver, turning it black. To protect these precious objects, photographers sealed the plates under a sheet of clear glass, held tightly by a decorative brass mat and foil preserver, and housed inside plush, velvet-lined leather or thermoplastic miniature cases known as union cases. From a purely scientific and physical perspective, the resolution of a daguerreotype remains staggering even by modern 21st century AD standards. Because the image is formed by microscopic chemical crystal growth at the molecular level rather than through macroscopic film grain or digital pixels, the detail is essentially continuous. When modern conservators examine a well-preserved 1840s AD daguerreotype under a high-powered optical microscope at 50x magnification, they can clearly read the maker's hallmarks stamped into pocket watch dials, count the individual fabric threads in a subject's silk vest, and see the tiny reflection of the studio's skylight window reflected inside the iris of the subject's eye. Despite its overwhelming optical perfection, the reign of the daguerreotype was relatively brief. The process had two fundamental economic and practical shortcomings. Each daguerreotype was a unique, direct positive with no negative, meaning it could never be duplicated or reprinted, and the polished silver plates were heavy, rigid, and expensive. In 1841 AD, English polymath William Henry Fox Talbot patented the calotype process, which used paper negatives to produce multiple positive paper prints, establishing the fundamental negative to positive concept that would dominate photographic history for the next 150 years. Then, in 1851 AD, an English sculptor and chemist named Frederick Scott Archer invented the wet collodion process. By coating glass plates with collodion sensitized with silver salts, photographers could capture images with the razor sharpness of a daguerreotype, but with the immense commercial advantage of being able to print unlimited copies onto albumen paper at a fraction of the cost. By the late 1850s AD and early 1860s AD, the daguerreotype had been largely superseded by glass negative processes, ambrotypes, and tintypes, fading into history as a magnificent shining relic of the early industrial age. Yet the impact of Louis Daguerre's invention on human civilization cannot be overstated. When the famous French academic painter Paul Delaroche Fischer first saw a daguerreotype in 1839 AD, he is said to have proclaimed in awe and despair, "From today, painting is dead." While painting did not die, instead freeing itself from strict realism to birth modern art movements like Impressionism, our relationship with truth, memory, and time was fundamentally and permanently transformed. For the first time in the history of our species, the passage of time could be arrested, and a slice of reality could be preserved with absolute optical fidelity. How did humans invent photography? It was not a sudden magical accident, but the culmination of 1,000s of years of human curiosity. It required ancient philosophers to understand the straight path of light, medieval Arab mathematicians to build the camera obscura, Renaissance masters to refine optical glass, 18th century AD chemists to discover the photosensitivity of silver, the relentless determination of Nicephore Niepce to capture the sun's rays on bitumen, and the relentless genius of Louis Daguerre to unlock the magic of the latent image in a vapor of mercury. Together, they gave humanity one of its greatest superpowers, the ability to hold a single fleeting moment of light in the palm of our hands forever.